The paper we're breaking down today is AlphaResearch, Accelerating New Algorithm Discovery with Language Models. If you're trying to keep up with autonomous agents, here is the 1-minute summary of why this paper is a big deal right now. So, the biggest hurdle for large language models has been discovering truly new algorithms. They just keep hitting two massive walls. One is verification bias, where an LLM judge just favors what it already knows.
And the other, which is huge, is the ideation-execution gap. Great ideas are one thing, but finding ones that are actually computationally feasible, that's the real challenge.
This is where AlphaResearch comes in. It's an autonomous research agent that introduces this novel dual research environment.
And this environment has two absolutely critical feedback loops. First, there's a simulated peer review system, which is basically a reward model trained on real scientific papers.
And the second?
A super rigorous execution-based verification system. It actually runs the code.
The whole thing is iterative. The agent proposes ideas, checks them in that dual environment, and then just optimizes the ones that work.
And the results, they're pretty shocking. AlphaResearch scored a 2 out of 8 win rate against professional human researchers on a new benchmark they built.
The highlight was definitely discovering a brand new algorithm for the packing circles problem, specifically for 32 circles. It hit a performance of 2.939, which beat not only the human baseline, but also other systems like AlphaVolve. It's real proof that these models can push the boundaries of what we know. That summary alone is, well, it's a lot to take in. It raises a huge question for me, though. If the goal is this kind of autonomous discovery, why is discovering the unknown still such a massive struggle for these huge models?
It really boils down to that synergy between, let's say, innovation and just plain reality.
Right.
As you said, that ideation-execution gap it's just lethal.
Right.
An LLM can spit out thousands of incredibly creative-sounding algorithms, but if 99% of them violate some basic math rule or need a supercomputer that doesn't exist, they're completely useless from the get-go.
And then there's the other side of the coin. If you use the classic LLM as a judge approach, where the model judges its own ideas.
It gets stuck in a rut.
Exactly. It throws out the truly novel ideas just because they don't look like the stuff in its training data. It kind of fails at what scientific peer review is supposed to do, which is balance the new with the rigorous.
That's the perfect way to put it. So AlphaResearch's main goal was to fuse those two skills together. Really aggressive idea generation and super robust, verifiable code implementation.
And that synergy is built right into its research loop.
Yep, it's an iterative loop.
So the agent is basically running this constant, tiny research cycle. Can you walk us through the 3 core steps it's using?
Of course. So step 1 is proposal. It generates new ideas, often using an ensemble of models, and it's heavily conditioned on its own history, what's worked, and just as importantly, what hasn't.
Okay, and then step 2 must be the verification part.
That's the core novelty, yeah. The verification happens inside that dual research environment. And then step 3 is optimization. It just refines the successful programs to squeeze out even more performance to get a higher reward.
And all of that history, the idea, the code, the final score, is packed into what the paper calls the trajectory. Is it fair to think of that as just a complete research diary?
That's a perfect analogy. That diary is updated constantly, and it means the next idea isn't just a random shot in the dark. It's grounded by what actually worked and what didn't in the real world, computationally speaking.
It's almost like reinforcement learning for doing science.
That's exactly what it is. The trajectory becomes the policy input that just keeps getting better.
That feedback loop sounds incredibly disciplined. And that brings us to the real breakthrough here. This dual research environment. It's not enough for code to just run, right? You need that scientific rigor.
This is where they really tackle that innovation versus feasibility trade-off. They built a simulated peer review system, which they call AlphaResearch RM7B.
An RM, a reward model.
Right? And its whole job is to filter out the ideas that are, creative but fundamentally flawed before you waste a ton of compute trying to run them.
How on earth do you train an AI to act like an academic peer reviewer?
You go to the source. They trained it on actual peer review records from ICLR.
The big machine learning conference.
Exactly. They scraped everything from 2017 all the way to 2024. Abstracts, reviews, scores, the whole package.
That's fascinating. So they fine-tuned a pretty powerful base model, Qwen 2.57b Instruct, on all that data. The goal being to predict the quality of a research idea just from the abstract, but how good is it really?
Okay, this part is genuinely astounding. They tested it on unseen data from the upcoming ICLR 2025 cycle. They defined a good idea as any paper with a review score over 5.5.
And the model's accuracy?
The AlphaResearch reward model achieves 72% classification accuracy.
72%. Wait, just to be clear, that means this specialized AI is better at spotting a promising research idea than an actual human reviewer.
It is. The numbers are a little scary, honestly. For comparison, they said a hypothetical GPT-5 only got about 53% accuracy, basically a coin flip. And the human annotators they use as a baseline, they only average 65%.
So it's not just better than a general-purpose LLM, it's measurably better than the domain experts.
Precisely. This specialized RM is a superior filter for research quality.
So if I'm understanding this, the reward model is kind of like the program manager or maybe the venture capitalist. It's filtering the pitches before the engineering team even sees them.
That's a great way to think about it. It's a gatekeeper. It makes sure that only the ideas with some scientific plausibility move on to the second part of the environment.
Which is the execution phase, where the rubber meets the road.
Exactly. This is where you get that verifiable reward. It's inspired by earlier work like AlphaVolve. It uses an evaluation program with two key parts.
Okay.
First, a verification module, which checks if the code actually follows all the rules of the problem, no cheating. And then a measurement module, which spits out the final score, that jerk value.
And that score, that hard number, gets fed right back into the research diary, into the trajectory.
And that's what drives the next round of ideas. You have this beautiful loop between a qualitative peer review style check and a hard quantitative reality check.
Which is key to generating ideas that are both innovative and, actually work.
It moves way past the problems that held back earlier systems.
So to prove all this, they needed a transparent playing field. You mentioned that systems like AlphaVolve didn't always publish all their test problems, which makes direct comparison hard.
Right, so they built their own. It's called the AlphaResearchComp benchmark.
And it sounds serious.
Oh, it is. It's 8 really hard, open-ended research problems. They cover geometry, number theory, combinatorial optimization. We're talking about things like packing circles, Littlewood polynomials, MSTD sets. Really tough stuff.
And the beauty of the benchmark is that all the problems have these precise mathematical objectives, so they can be evaluated automatically.
And, crucially, they all have known human best baselines. But here's the clever part. A lot of those baselines are just conjectured to be the best. They aren't proven optima.
So they deliberately left room for the AI to find something better.
Exactly. It's a perfect setup to test for a true breakthrough. And to measure that, they use a metric called excel at best.
Okay, so excel at best isn't just about winning or losing. It's a standardized way to measure how much better your new solution is.
You've got it. It's the percentage of improvement over the human baseline. It lets you compare performance across totally different problems in a uniform way. It's a measure of true superhuman performance.
And this brings us to that headline result we mentioned, the 2 out of 8 win rate. Let's focus on the big one, the packing circles problem for n equals 32. Why is this such a breakthrough?
Because the agent found a solution with a sum of radii of 2.939. This is a new definitive state of the art.
And the old record.
The best human design solution was 2.936. AlphaVolve had managed to get it to 2.937. So AlphaResearch didn't just find a small improvement, it found a fundamentally new arrangement that pushed past the best results from both humans and previous AI systems.
A new soda discovered completely autonomously. That's a massive win for this whole dual environment idea.
And you can see that autonomous refinement across the board. Even on problems that didn't win, 6 of the 8 showed this consistent upward trend over thousands of iterations. The score just kept climbing.
Like a real research team slowly chipping away at a problem.
Exactly. A rapid climb at first, then a slow plateau as it gets closer to the optimal solution. It's the signature of the process working.
Okay, but now we have to talk about the flip side, the 6 out of 8 failure modes. Even with this powerful setup, it still underperformed humans on most of the benchmark. Why?
This is really important for understanding the current limits of these agents. The paper notes something really interesting. When they initialized the agent with the absolute best human solution for problems like Littlewood polynomials,
The agent got stuck.
it completely failed to show any measurable improvement. The reward just flatlined.
So when the solution space has already been super optimized by humans over decades, the agent struggles to find that next innovative leap.
It seems so. It suggests that while its exploration is great from a cold start, it might be too conservative, maybe the steps it takes are too small, when it's already standing on the shoulders of giants.
And speaking of what guides those steps, That reward model, the ablation study, really hammers home how valuable it is.
Oh, massively. It's not just about accuracy, it's about saving an incredible amount of wasted computation.
Right.
Just on the packing circles problem alone, if they turned off the RM, the agent would have tried to execute 151 ideas that were doomed from the start.
And the RM caught how many of them?
It correctly rejected 71.5% of those failing ideas. That's a huge real-world saving in compute time and cost.
It's more than just a filter, though, isn't it? The paper says the ideas generated with the RM were just better.
They were. They scored higher on the RM's quality scale compared to ideas from an execution-only agent. So that peer review filter is actively steering the agent towards more promising parts of the search space. It's not just filtering junk, it's encouraging quality.
So as we look forward, where do the authors see this going next? How do we make these agents even better?
They point to a few key areas. First, expanding the scope to more, realistic applications. They specifically mention accelerating tensor computations, which is at the heart of all modern ML.
That would be a huge deal. And I assume adding external tools is on the list.
Yep. Letting the agent use web search, calculators, other computational tools, that's a natural next step.
And the reward model itself.
There's plenty of room to grow, a bigger model, a much bigger data set. Right now it's trained on about 24,000 ICLR records. Scaling that up could create an even more powerful and generalizable scientific judge.
So the big takeaway for anyone listening who's in this technical space is pretty clear. AlphaResearch shows a really feasible path forward for autonomous algorithm discovery.
It's a blueprint. By merging that simulated peer review with hard-nosed program execution, they've shown how to generate ideas that are both truly novel and actually viable.
It validates the idea that if you structure an LLM's process to mirror how science actually gets done, you can get results that beat the human state-of-the-art.
It really moves the LLM from being just a tool, like a fancy code generator, to something closer to a genuine autonomous research partner.
Which leaves a really big question for you to think about. If an AI agent can now find best-of-known solutions in a field as complex as combinatorial optimization just by mimicking our own research process, what field of research, maybe one outside of computer science, is going to be the first to see its human soda consistently broken by one of these agents? What will the next peer review RM unlock?